Right triangle trigonometry is the trigonometry that you did in your geometry classes. So, most of the stuff you're going to see today and tomorrow, because tomorrow is also 12.1, most of the stuff you've seen before. There are a couple of things you haven't. First off, to get on the same page, what is trigonometry? Anyone remember when to use trigonometry? Because that kind of gives you what trig is. Has to deal with angles and triangles. Cosine and sine are some trig ratios. It's not only angles, though. Trig also uses, what's the other things in triangles? There's angles and then there's sides. And there's one other key feature. We've almost hit on all of the things that go into trigonometry. Triangles, angles, sides. Just one other key feature.
Points.
No. What kind of triangle?
Acute.
Right triangles. So trigonometry, by definition, is the study of the relationships between sides and angles of right triangles. Now, this definition actually more accurately comes from the origin of trigonometry. Trigonometry was originally created specifically focusing in on right triangles. But as we are going to find in this class, it has been expanded into working with more than just right triangles. Let's just go with that. But it all is based in initially working with right triangles, which is the trigonometry that you do in geometry as you focus in on those right triangles. And when you do trigonometry, you have trigonometric ratios. Or trig ratios. Oh, can I make it fit? No. Trig ratios, really, they're the side length comparisons based on an angle of the right triangles. Now, specifically not the right angle. Essentially, trigonometry was born with this idea that when you have a right triangle, due to similarity, if you know what one of the angles is, you actually know a comparison of all three sides of the right triangle, because of the fact that as you work with a similar triangle, which is essentially just a bigger or smaller version of it, the angles within the triangle end up being the same, and therefore the ratio, the fraction made with the side lengths, ends up being proportional. And so someone took out and said, okay, we know all of those proportions and we can note exactly what they are. Trigonometry used to be done with this big old chart, similar to your normal chart, that had all of trig on it. Sine, cosine, tangent of every single one of those angles. Now, That's pre-me learning how to do math, but it started there. Now, in geometry, you worked with three main trig ratios, and I have already said that. You worked with sine, cosine, and tangent. These are the three main trig ratios, but it's not the only trig ratios. These are generally the ones we work with when we're doing right triangle trig, but there are a total of 6 ratios. Because when you work with a triangle and you're comparing sides, you're making fractions out of the sides. There are 3 sides, and you can make more than 3 fractions. You can make 6 in making fractions of a side length to another side length of the triangle. So there's technically 3 more trig ratios. Now before we get to those 3, one of the most important things that we're going to need is we're going to have to talk about these 3 and the fact that they have a shortened version of each of them. Sine in a shortened version is sin. Cosine in a shortened version is cos. Tangent is tan. Do you notice that I did not say sin, cos, and tan? It is not sin, cos, and tan. If you had me in Geometry B, you have heard this rant before. It is not sin, cos, and tan. It is sine, cosine, and tangent. We shorten them down for the ease of writing, but we still say sine, cosine, tangent. Now, these ratios are based on an angle. And before I get to the other 3 ratios, we got to focus in on that angle, and we have to focus in a little bit on how sine, cosine, and tangent work. Now, back in geometry, with sine, cosine, and tangent, you would have learned like a tool to kind of help you with sine, cosine, and tangent. Almost like a gibberish word. 3 parts to it. SOHCAHTOA. Sound familiar? Does anyone remember how to spell SOHCAHTOA? SOHCAHTOA. Do I typically get picky about spelling in this class? No. SOHCAHTOA, you better spell right though, because SOHCAHTOA only means something if it's spelt correctly. It means nothing if it is not spelt correctly. SOHCAHTOA. Now, there's one other thing that we need to talk about before we break down SOHCAHTOA, before we break down sine, cosine, tangent a little bit more, before we get to those last 3 trig ratios, and that is we want to focus in on the angle itself. Now, when it comes to angles in this class, dude, no one's going to answer the calculator. Stop putting it to your ear like a phone. When it comes to angles in this class, when you were in geometry, generally, if you didn't know what an angle was, they just put a variable like x there. Generally speaking, as you get into more advanced math, you'll find that there is one variable that is almost always used for angles. And it's this variable. Anyone ever seen it before? It's Greek letter theta. So it's the Greek letter, or in this case, Greek, we're using it as a variable. And it's used to represent unknown angles. You can still technically use other variables to represent angles. Most commonly, it's not done that way, though. So they use theta. Now, let's talk about SOHCAHTOA a little bit. Let's talk about sine, cosine, tangent. So, first off, when it comes to trigonometry, the way that trig is always set up, these ratios, they are always set up as the trig ratio of an angle equals a fraction of the sides. That's how right triangle trig works. So, sine of some angle, theta, is equal to something. This is where the SOHCAHTOA comes in. Sine is the S in SOHCAHTOA. It is followed with O and H. Does anyone remember what the O and the H represent? The O and the H are opposite and hypotenuse in a right triangle. Get your right angle, get your hypotenuse. You've got your two acute angles, and your two acute angles are generally what you do the trig of. I'm going to call this one theta. The other two sides, the legs, are called the opposite and the adjacent. Opposite is across the triangle from the angle you're using as the point of reference, because trig is always referenced back to an angle. If we're going to use theta as our point of reference, I go across the triangle, I get to this side, and that is the opposite. The leg that is connected to the angle that you're using as your point of reference is the adjacent. Keep in mind, opposite and adjacent will change depending upon which angle you're focused in on. If I was focused in instead on this angle being theta, this would be my opposite, this would be my adjacent. The hypotenuse always stays the longest side or the side across from the right angle. So far, is this looking familiar? Okay, SOHCAHTOA. Sine is opposite divided by hypotenuse. That's what SOHCAHTOA is trying to tell us. It tells us the trig ratio, and it is equal to the middle letter is the side and the top of the fraction, and the second letter is the side and the bottom. Sine is opposite divided by hypotenuse. Cosine of theta. AH tells us that is the adjacent getting divided by the hypotenuse. Tangent of theta. That's the TOA piece, T-O-A. O tells us it is opposite, getting divided by A, adjacent. These are the three main trig ratios, but as I have stated already multiple times in this class, they're not the only ones. We've got three more trig ratios, because you can make three other fractions when I have opposite, adjacent, and hypotenuse. What other fractions can I create? Instead of opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, what other ways can I divide these side lengths? I'm hearing some little whispers, but I have no earthly idea what any of them are actually saying. Adjacent over opposite. That's one of them. Hypotenuse over opposite and hypotenuse over adjacent. Those are the other three trig ratios. Hypotenuse over opposite. Hypotenuse over adjacent. And adjacent over opposite. How are these three related to the original three? They're the flipped version. What do you call flipping a fraction? They're the reciprocals. These three, which I have not named yet, are known as the reciprocal trig functions. They are the flipped version of the original three. That is why in geometry you didn't learn them, because you didn't really need them for what you were doing at the time. As you get into more and deeper mathematics, where we're doing non-right triangle trigonometry, they start having a purpose. Now when it comes to these reciprocal trig functions, hypotenuse over opposite is the reciprocal of which one? It's the reciprocal of sine. How do you write something's reciprocal? What's the reciprocal of 2? 1/2. What's the reciprocal of 5? 1/5. What's the reciprocal then of sine? 1 over sine. That's one way to write out its reciprocal. So this one is technically 1 over sine of theta. Hypotenuse over adjacent is the reciprocal of which one? Cosine. Therefore, it is 1 over cosine of theta. Adjacent over opposite is therefore 1 over tangent of theta. Now, I emphasize this fact, 1 over sine, 1 over cosine, 1 over tangent. I emphasize the reciprocals, something is the reciprocal of, a lot more than hypotenuse over opposite, hypotenuse over adjacent, and adjacent over opposite. Because it's a heck of a lot easier to know your SOHCAHTOAs and then flip them. But let's get back to what these three are named. These three are named cosecant, secant, and cotangent. Cosecant is CSC, secant is SEC, and cotangent is COT when shortened. I write them in this order for a reason, because it gives us that reciprocal relationship written out. Now, when it comes to this class, knowing your SOHCAHTOA, knowing sine is opposite over hypotenuse, cosine's adjacent over hypotenuse, tangent is opposite over adjacent, knowing this is going to be a key thing that you just need to know. It is not something that you need to be in a position to look up every single time. If you have to look it up every single time, to be blunt, you're screwed. It's something we're going to need to memorize, SOHCAHTOA. Another thing that you should memorize is which trig ratio is the reciprocal of which one. So, first off, when it comes to knowing this, do you notice that an old one is paired with a new one every single time? In each pairing, sine, cosecant, cosine, secant, tangent, cotangent. I don't know if there is a better way to memorize it, but I kind of go with two things. First off, tangents are the only ones that go together with the ones that is of their name. Tangent, cotangent. Otherwise, they don't go with the same name. I need new with old. Sine doesn't go with cosine. Secant doesn't go with cosecant. But the tangents go together, tangent to cotangent. And then in their pairings, only one in a pair will have co in it. Sine needs to go with something that has a co in it because sine didn't have co in front of it. The only new one that has co on it that's not tangent, because tangent and cotangent go together, is cosecant. Cosine already has a co in front of it, needs to go with one that doesn't have a co. The only new one without co, secant. And then the tangents go together. That's how I use it. Is that going to be the way that works best for you? I don't know. But only one of them has a co, and as a result, if it helps you looking at their shortened version, only one of them in every pair starts with a C. Because of that piece. You can use this information, the hypotenuse, the opposite, the adjacent, to work with your reciprocal functions as you get going. If that makes it easier for you to start off, go for it. Cosecant's hypotenuse over opposite. Secant is hypotenuse over adjacent. Cotangent is adjacent over opposite. But as we continue through, you need to kind of move away from needing this for your reciprocals, because it's going to be a lot more powerful for you to know what it is the reciprocal of, and therefore which fraction you flip over. So, today, you're going to see problems that are going to ask you to find the ratios. We're just focusing in on finding our fractions today. We're not doing any sort of solving with it. Just finding our fractions. You're going to see questions that come in two different formats. Through two main formats. First format is going to be something along the lines of find the 6 trigonometric ratios for the triangle based on theta. Yes, it might say trig ratios. It might not always be theta. But it's going to tell you based on a specific angle, because if they don't tell you which angle to start with, then you got an issue. Now, speaking of issues, I didn't put theta in the triangle. I should probably do that. This option will be accompanied with a picture of a triangle. So I want my 6 trig ratios. Sine, cosine, tangent, cosecant, secant, and cotangent. That's where SOHCAHTOA comes in, and knowing which one's the reciprocal of which one. But we're missing something. Can anyone tell me what we're missing? A side. We're missing one of the sides. We are missing one of our sides, and therefore we cannot write all 6 of the fractions. So we got a problem. If I don't know something, I put an X on it. If only I knew a way to find a missing side length of a right triangle. A squared plus B squared equals C squared. Pythagorean theorem. Now in order to do Pythagorean theorem, I do need to identify which side is the hypotenuse. In this case, 50. It's across from the right angle. So x squared plus 48 squared equals 50 squared. Do you notice that nowhere it talks about doing anything with rounding? Which means I want exact. Generally speaking, in this class, if I want a decimal answer, I will tell you what to round to. Otherwise, we're looking for exact answers. Okay, what is 48 squared? 2,304. It's 50 squared. 2,500. Subtract the 2,304. X squared is equal to 196. To get rid of the squared, I take the square root. Do I need a plus or a minus here? Nah, it's triangles. X is equal to 196 is a perfect square. 14. Before you start looking for things that divide out, make sure you check if things are perfect squares, if they're bigger than the perfect squares you know. Okay. So, now I do know that this side is 14. Now I can start writing my trig ratios. When you are writing the trig ratios, again, I'm going to emphasize, it goes trig ratio of an angle. You do not just write sine or sin, it is sine of the angle you're referencing, in this case, theta. Cosine theta, tangent theta. I start with my SOHCAHTOA. In order to do SOHCAHTOA trig, though, I need to recognize not only hypotenuse, but the opposite and the adjacent. Which side of this triangle is the opposite? The 14 is the opposite. It's the leg that is across from the angle. The leg that is next to the angle is the adjacent. Adjacent literally means next to. Okay, SOHCAHTOA. How do you spell the beginning of it? S-O-H. Sine is equal to opposite divided by hypotenuse. Opposite is 14. Hypotenuse is 50. As always with fractions, simplify if possible. Seven over 25. Cosine. Ka. How do you spell ka? C-A-H. Adjacent over hypotenuse. 48 over 50, simplify a fraction. 24 25ths. Tangent. Toa. Opposite adjacent. 14 over 48, simplify a fraction. 7/24. Okay, those are my first three. To get the other three, I go with reciprocals. Sine's reciprocal is, well, it doesn't have a co on it. It doesn't start with C, so I know it's one that has to start with C. It's one of my new ones. It is cosecant. Now you can go through and you can say, okay, cosecant is hypotenuse over opposite, and therefore I do 50 over 14, and then I simplify my fraction. Or we said it was the reciprocal of sine. We also said sine was 7/25. What's the reciprocal of 7/25? 25 sevenths. Cosine's reciprocal. Well, it starts with C, which means I need one that doesn't start with C. What's the only new one that doesn't start with C? Secant, S-E-C. Reciprocal of 24 25ths? 25 24ths. Tangent doesn't start with a C, so I know its reciprocal does. Tangent's reciprocal is cotangent. Reciprocal of 7/24, 24 sevenths. Yes? No. I'll show you the top of it later so you can get the rest of it. Okay, so that's one form of question you're going to be asked. Second form of questions you're going to be asked today is going to look similar but a little different. This one's going to say, find the 5 remaining trig ratios. And then it's going to give you a trig ratio. I'm going to give you tangent of A is equal to 2/11. Specifically, where A is an acute angle. If A is not an acute angle, we have a different approach to this problem that we will not talk about for a while, honestly. I'm giving you a trig ratio, which means I'm giving you information essentially about a triangle. Specifically, I know it has to be a right triangle. Draw myself a right triangle. I know on this right triangle there's going to have an acute angle A in it. So I'm going to go to one of the angles. I'm going to call it A. Now note that it is a capital letter. That means they're naming it like a vertex, like we did back in geometry. When you named shapes, you'd put capital letters on the corners. Inside, you could put variables if they were variables. A is not a variable. A is the name of the angle. Now, about this triangle, we know the tangent of that angle A is 2/11. What do you know about tangent? Opposite over adjacent, right? That's the opposite. That's the adjacent. Now, in all technicality, that's not 100% true. It's not 100% true because of the fact that, for example, on the previous problem, tangent was 7/24, but were the side lengths 7 and 24? No, technically we simplified the fraction to get that. This one might be a simplified fraction to get that, but did you also notice that all the fractions really kind of simplified in the same way? And generally speaking, that's going to hold true. So it's going to help be just fine to call that the opposite, that the adjacent. Which side is the opposite? The vertical one, the horizontal one, or the slanted one? Horizontal. That's the opposite. Therefore, that is 2. The adjacent, is it the vertical or the slanted? Vertical. The slanted is the hypotenuse. I want I want all trig ratios. I want the 5 remaining trig ratios. If I want the 5 remaining trig ratios, don't I need all 3 sides? A squared plus B squared equals C squared. Once you have the triangle drawn out, you're doing the exact same thing as what you already did. The only thing really different at this point is you probably don't need to tell me what tangent is, because I started you with that. I'll put an X here. It's the hypotenuse, so 11 squared plus 2 squared equals x squared. 11 squared is 121. 2 squared is 4. Add those together, I get 125 is equal to x squared. To get rid of a squared, I take the square root. Square root of 125. Divides by what perfect square? $25. It is 25 times 5. So square root of 25, square root of 5, aka 5 root 5. Once I have all 3 sides, I go through and do my SOHCAHTOA. Sine of A this time equals opposite 2 over hypotenuse. 5 squared is 5. Can I simplify that fraction? Yes, because you cannot leave square roots in the denominator. How do I get the square root of 5 out of the bottom of the fraction? Times both top and bottom by root 5. Two times root 5? 2 square root of 5. Over 5 square root of 5 times square root of 5? 5 times the square root of 25, and the square root of 25 is 5. So I end up with 5 times 5 in the denominator, which is 25. The one thing that I recommend that you do, especially on these ones where you're having to go through and do some simplifying, make sure it is clear which trig ratio goes with what answer. Like on my previous one, it was really straightforward, really easy to see what went with what. As these get more complex, you might need to move your sine of A down. Okay, that's sine. Cosine. What side over what side? Adjacent over hypotenuse. 11 over 5. Square roots of 5. Can I leave the square root of 5 on the bottom? No, I multiply both the top and the bottom by square root of 5. $11 times square root of 5 is 11 square roots of 5. 5 square roots of 5 times the square root of 5. We did that already on the first one, and it ended up being 25. 11 25ths does not simplify, just like 2 25ths did not simplify on the last one. That's why I didn't go any further. If the whole numbers simplify, make sure you do it. Sine, cosine, tangent. Do I need to do tangent? No. Tangent is what I gave you in the first place. Can you write it down? Yeah. Is it excessive? Yeah. Okay. So sine, cosine, tangent, and now the reciprocals. Sine's reciprocal is which one? The one that goes CSC, it's cosecant. Okay, here's the thing about doing the reciprocal. Do you notice I have 3 different versions of what sine is? Some simplified, some not. If I flip the most simplified version, that 2 square root of 5 over 25, I end up with 25 over 2 root 5, and then I'm going to have to rationalize the denominator again. In other words, get rid of the square root at the bottom. But if I take the original and flip it, do I have to worry about the square root in the bottom? No. It's already simplified for me. When you have these ugly looking ones, oftentimes if you had to rationalize the denominator, flip the original. You're saving yourself some work. The original sine of A was 2 over 5 root 5, so I'm going to do 5 root 5 over 2. Still double check. Can I simplify that? No. Sometimes you will be able to simplify it still, but it's going to be in the situations where the 5 and the 2 simplify. You don't have to rationalize again. Okay, that's 3 of them. I need 2 more. What's cosine's reciprocal? Secant. S-E-C. I could flip this one, but it's better off to flip the original one. Save myself the headache. 5 squared roots of 5 over 11. It's the last trig ratio. Cotangent. How the heck am I supposed to do cotangent of A if I didn't find tangent of A? It was given to you in the question. Flip 2 11s, you get 11 halves, which doesn't simplify. Second problem, all that different from the first problem? No. Yep. Okay, we are on page 795. As always, when I write down day 1, please write day 1 on your homework assignment. That means we're going to be on 795 as well tomorrow. It is question number 13 through 20.